We've all seen the sci-fi art. A massive, flawless cosmic cage wrapping around a star to catch every single photon of its energy. The ultimate trophy of a civilization that has officially beaten the game of evolution. In fact, just recently, an international astronomical survey called Project Hephaestus scanned millions of stars and claimed to find 7 potential Dyson Sphere candidates. For a brief moment, humanity gasped. Did we find them? Well, update your sci-fi journals, because data from the James Webb Space Telescope and high-resolution radio grids just delivered a massive reality check. It turns out those megastructures were just ultra-distant, dust-choked galaxies sitting directly behind normal stars, blinding our sensors with fake infrared excess. Space, once again, remains a lonely, silent void. But this disappointment forces us to face a much bigger, physics-approved truth. The classic sci-fi vision of a solid Dyson sphere isn't just missing. It's mathematically and physically impossible. If you tried to build a solid shell around the sun, the universe would dismantle it within minutes. Welcome to the cosmic grind. Today, we are breaking down the terrifying engineering reality of how you actually steal the power of a star. Let's look at the blueprint. Freeman Dyson originally popularized this idea in 1960. He imagined a rigid shell sitting at 1 astronomical unit from the Sun, right where Earth sits. Sounds great on paper, but here's the problem. A solid sphere enclosing a star has zero net gravitational interaction with that star. This is a neat trick of physics called the shell theorem. In plain English, the Sun doesn't hold the sphere in place. If a stray asteroid nudges your multi-trillion-ton megastructure, or solar wind pushes slightly harder on one side, the whole thing shifts. And that tiny shift is enough to make the system catastrophically unstable. Since there is no restoring force pulling the shell back to the center, it won't stop. It will just keep drifting. As the distance closes, the side facing the Sun is exposed to rapidly increasing radiation and heat, placing enormous thermal and mechanical stresses on the structure. Without constant active thrusters correcting its position, this engineering marvel would eventually slide through the void and collide with the star itself, turning the greatest construction in history into a multi-trillion-dollar campfire. But hey, you say, why not just spin the sphere to stabilize it with centrifugal force? Nice try, but physics doesn't care about your feelings. If you spin the sphere, only the equator gets that outward push. The poles remain completely stationary. Gravity would instantly crush the top and bottom of your sphere inward, turning your beautiful cosmic bubble into a sad, deflated metal pancake. To build a megastructure that doesn't commit suicide, we have to ditch the solid shell and embrace the Dyson Swarm. Instead of one giant piece of metal, we need billions of independent, ultra-thin solar-collecting satellites, essentially solar sails, flying in coordinated orbits. Each one harvests energy and beams it back via wireless microwaves. But now we hit the real boss fight of this project, the raw material crisis. To build a swarm thick enough to actually capture a significant amount of sunlight at Earth's distance, you need a mind-boggling amount of matter. If you dug up the entire Earth, every mountain, every ocean, the iron core, your neighbor's house, and flattened it into solar collectors, you would only have enough material to build a shell about a few millimeters thick, and worst of all, you'd have no planet left to live on to enjoy the power. Fortunately, a Dyson Swarm doesn't need to be a complete shell. Dismantling even a single planet could provide enough material to harvest a substantial fraction of the Sun's power. So, to build the Dyson Swarm, we have to find a sacrificial lamb. And looking at the solar system's map, scientists have unanimously pointed at the closest, most useless rock available: Mercury. Mercury is a paradise for cosmic strip mining. It's practically a giant ball of iron and heavy metals sitting right next to the construction site. It has no atmosphere, low gravity, which makes launching materials into space incredibly cheap, and it's already completely uninhabitable. Sorry, Mercury, you're being reassigned to become a solar panel factory. How do we actually dismantle a planet? Humans are once again far too squishy for this. The surface of Mercury faces brutal radiation and temperatures that melt lead. This is an entirely automated exponential job for self-replicating AI robot swarms. First, we land a modest fleet of automated miners and solar-powered factories. They mine Mercurial iron, process it, and build two things: more factories and ultra-thin, lightweight mirrors made of aluminum or carbon graphene. Once a mirror is built, it doesn't need a heavy rocket to launch. Mercury's low gravity allows us to use mass drivers, giant electromagnetic railguns. These railguns launch the solar sails into orbit using pure electricity. This is where the magic of exponential growth happens. The first few thousand solar sails launch into orbit and begin beaming power back down to the factories on Mercury. With more power, the factories build more automated miners and more railguns. The production speed doubles. Then it quadruples. Within a few decades, the entire planet of Mercury becomes a giant, whirring, self-eating machine, literally chewing itself from the inside out and spitting its own corpse into space to wrap around the sun. Which is pretty much what my crazy ex would have done to me given the chance. Once the Mercurian grind is complete, humanity officially ascends to a Kardashev Type 2 civilization. We are no longer planetary peasants scraping for oil and lithium. We now control the full energy output of our star, roughly 3.8 times 10 to the 26th power watts of power. To put that into perspective, that is about 1 trillion times more energy than the entire human race consumes today in a year. What do you even do with that much juice? With a Dyson Swarm, energy becomes effectively free. We could power literal matryoshka brains, stellar-sized supercomputers capable of simulating billions of virtual universes or uploading human consciousness into an immortal digital heaven. We could power relativistic laser highways, physically pushing interstellar colony ships to neighboring stars at a fraction of the speed of light, without them needing to carry a single drop of fuel. We could reshape entire planets, melt ice moons, and turn the solar system into our personal sandbox. Which makes you wonder just how huge of a graphics card Jensen Huang is going to build now. The solid glass domes of Sci-Fi are dead, replaced by the chaotic, beautiful reality of a billion flying mirrors. Building a Dyson Swarm isn't a quick weekend project. It's a multi-generational, planetary-scale commitment to absolute optimization. And this brings us back to the ultimate question: the Fermi paradox. If megastructures like this are the logical end state of any advanced civilization, why is the sky so quiet? Are we truly the first ones to reach for the stars? Or do civilizations inevitably collapse before they can light up their solar systems? We haven't found a Dyson Sphere out there in the dark yet, but maybe that's because the universe is waiting for us to build the first one. While our automated AI factories are still waiting for their ticket to Mercury, you have just enough time to smash that like button, subscribe to the channel, and leave a comment. Would you upload your brain to a stellar supercomputer or stay on Earth? Stay curious, and I'll see you in the next simulation.